Hey everyone, welcome into this lecture on Newton's law of cooling. In the last lecture we talked about the exponential growth and exponential decay equations, and in this lecture we'd like to talk about Newton's law of cooling. So basically what does Newton's law of cooling says? It says that the rate of cooling of an object is proportional to the difference between the temperature of the object and the temperature of the ambient air. So what do I mean here? Well, I'm going to draw, this is going to be like a brick of tofu or something that's just come out of the oven, and you set it on a counter, and you want to, you say, all right, the temperature of this thing is T, so this T of little t, big T of little t, this is equal to the temperature of the object at time t, time little t, all right, and usually for us, little t is going to be measured in hours. So it doesn't have to be though, so we can deal with that. But let's suppose that it's measured in hours, and then T sub S, this is going to be the temperature of the surroundings. And so this is called the ambient temperature sometimes. So the temperature of the surrounding, and this T sub S is equal to a constant. So we're going to assume, at least for the sake of this lecture, that the ambient temperature is not changing. So that the ambient temperature is constant, and the temperature of the object is going to change, right? And again, what Newton's law of cooling says is that the rate of change of the temperature of this object, this tofu, which I've drawn so beautifully here, the rate of change of this is proportional to the difference between the temperature itself and the ambient temperature. So that's going to be T minus T sub S. All right, and so by the way, if this difference is negative, then actually the law of cooling says that the tofu in this case is going to heat up, right? The object is going to be heating up. Yeah, so this is the differential equation. This, by the way, it is possible, okay, that we can rearrange this slightly, all right? So let's say we want to get this to look, this should remind you of the exponential growth and exponential decay problem, at least the equation that we did before. It's just slightly different, right? So we can make it look like that, right? So let's say we let y equal t minus t sub s, right? So t minus a constant. Then what's t equal? T is equal to y plus this ambient temperature, right? And look what happens if we take our derivative. Derivative of t with respect to t is the same as the derivative of y with respect to t, because this is a constant, right? So the derivative of this is 0. And so this entire law of cooling can be thought of as an exponential growth or exponential decay problem, where the derivative, dy dt, is equal to k times y, right? K times y. Yeah, and then we just have to make this substitution at the end, all right? So let's do an example. And you can think of this any way you want, right? By the way, usually when you do an example, you're going to have some initial temperature. We talked about that actually, right? So initial temperature, and then you plug in the values to answer some question about, yeah, well, let's just do an example, all right? So here's an example. Let's stick with the tofu, why not? So let's say we take our tofu out of the oven at 450 degrees. So 450 degrees Fahrenheit out of the oven. We set it on the counter in the room, so the room's temperature is going to be set, let's just say like a normal room temperature, around 73 degrees Fahrenheit. So we're going to call this the constant, just to remind ourselves, ambient temperature. Ambient means surrounding. All right, and then let's say we know a little more information. Let's say we come back in 30 minutes. In 30 minutes, we take the temperature of the tofu, and we find that the temperature, T of 30, so I've done this in minutes. I don't want to use minutes. I want to use hours. So let's say T of 1/2, half an hour, right, is equal to 350 degrees Fahrenheit. All right, and here's the question. How long do we need to wait until the temperature of the tofu is down to 200 degrees Fahrenheit? So how long must we wait for the tofu to be at 200 degrees Fahrenheit? This is the question. Panda, my dog Panda in the background is trying to help. So here's what we got. We are going to set up this equation. So I'm going to do this in terms of y, because we know exactly how the y works from our last lecture, right? So remember, y is the temperature, T sub T, minus T sub S, right? So this just means, really what this means is that we have to always factor in this ambient temperature, right? So this means that our initial temperature, when we do this, right, our y sub 0 is no longer going to be 450, right? It's going to be y of 0, which is 450 minus the ambient temperature, if I'm doing this, right? Minus 73. And so then this is going to be what? So that's going to be 377 degrees Fahrenheit. So there's our initial temperature. And we have to do the same thing with this, right? So then y of 1/2, half an hour, is going to be T of half an hour minus our ambient temperature. So I should write it that way. Minus T sub S, which is going to be, in this case, 350 minus 73 degrees. And so this should be 277. All right, and so let's plug in and find out. So with this equation, we know exactly what the solution is, right? Our y of t, in this case, instead of x, is equal to our y naught. This is from the last lecture, so if you don't remember this, just check it out. Why not e to the kt, right, where t is the variable. So this was an x in the last lecture, but t represents time now, so this is this. We don't know k, right? We don't know k yet. We do know y naught. Y naught is 377. So this is 377 e to the kt. And we can now use this information, the y of 1/2 equals 277, to try to solve for k. Or not to try, to actually do it, right? To solve for k. So y of 1/2 is equal to 277 on one hand. On the other hand, it's equal to our function, right? 377 e to the k over 2. And now we just need to rearrange this, right? So what do we have? We're going to solve this equation, solve for k. And so what do we get? We get e to the k over 2 equals 277 over 377. These numbers are weird. That's fine, right? To get the k out of the exponent, we now have to apply natural log. All right? And so now we have k halves equals the natural log of this ratio, 277 over 377, or k is equal to 2 times the natural log of 277 over 377. We can do even more here if you want. I mean, let's leave it like this for now and just see what happens. But remember, you can obey all the log rules, right? So this 2 can go upstairs, and you can square this. I'll write it down. So this could be the natural log of 277 over 377 quantity squared. Okay, and so let's plug this back in, because remember, now our goal is to find out at what time little t, that's basically how long must we wait, right? So this is little t equals question mark for the temperature, capital T. So capital T of t should equal 200, right? So this is our question. We now need to reframe this, since I've gone and changed everything to y. We should reframe this in terms of y, right? And so if big T of t is equal to 200, little y of little t is equal to 200 minus 73, right? We can't forget that that's what we're doing here. And so this is then going to be what, 127, right? 127 degrees Fahrenheit. So that's our target temperature, or at least our target value for capital Y. So let's plug back into our equation. We have y of t is equal to 377 e to the k over 2t. So I'm going to go back to this one, right? So e to the k over 2. Whoops, oh no, that's not right. E to the kt. Yeah, let's go with this one. I'm looking at the wrong thing here. So e to the kt, that's this one. E to the kt, and then we know what this is, right? So 377 e to the natural log of 277 over 377 quantity squared times t. All right, but look what happens here. We can use our exponent rules, right? And then this log will cancel with this. And we can rewrite this entire equation, y of t equals the log, the exponential cancels. So we have 377 times 277 over 377 to the power 2t. To the power 2t. And we want to set this equal to 127, right? That's our goal. 127, and then try to solve for t. All right, and so this now becomes our problem. So now we want to solve for t. Before we can solve for t, we need to, rearrange, get this 377 out of here. And so we get this equation. So 277 over 377 to the power 2t should be equal to 127 over 377. I left some room here because now we're going to apply the natural log to both sides. And the reason we do that now is because this can then come down, right? And so here we have 2 times t. Really, you can just bring, yeah, it's fine. 2 times t times this natural log, 277 over 377, equals natural log of 127 over 377. All right, these numbers are a little messy, but we're going to get it now. So our t is going to be equal to 1/2 of this ratio. So log of 127 over 377 divided by log of 277 over 377. This, remember, can be written as 1/2. So this could be written as log, just apply the log rules here. 127 minus log of 377, all divided by 2 times this log of 277 minus log of 377. And this one is probably going to require some calculator if you want to get an accurate reading on it. So let's go over to back over to our Sage here and type it out. So we need parentheses, right? ln of, this was 127 minus ln of 377 divided by 2 times ln of 277 minus ln of 377. And then we want this to be a decimal. There we go. So 1.765. This is in hours, right? So let's just round this to 1.77. 1.77 times 60 minutes. Let's find this out in minutes. So it's about 106 minutes. So it's about an hour and 46 minutes, right? So this turns out to be about equal to, so the time that we have to wait, right, is about equal to 1 hour 46 minutes. So this is just by careful calculation, and then at the very end you plug in, you keep everything exact until the very end so that you don't make any mistakes. But in about an hour and 46 minutes, your tofu will be at a desirable temperature to eat, presumably. That's what 200 degrees Fahrenheit is, given this problem. So yeah, that's Newton's law of cooling, and I'll see you guys in the next video.